If you follow along with me, I can assure you that you will be having a solid understanding of aerodynamics, the basics of engineering, and rocket science. Previously, we have seen the doping of semiconductor, in our case silicon. Now let us see what happens if the current passes through the p-n junction diode that we discussed in the previous video. Let us connect the negative terminal or anode to the p-type and connect the other positive terminal to the n-type semiconductor. The electrons in a circuit flow from negative terminal to the positive terminal due to the voltage difference, and this voltage difference increases the electron migration from arsenic to boron, which will lead to the increase in depletion region, and eventually the ions to carry the current reduces too, which results in an increase in resistance to the flow of electricity. A diode is represented in the circuit as shown. Now let us connect the cathode or positive terminal to the p-type and the negative terminal to the n-type. The voltage difference will move the electrons which migrated from arsenic back to the arsenic itself. Thus the depletion region reduces and the conductivity increases. I mentioned conductivity, how current is conducted, how this diode mechanism produces light. To answer these questions, we need to know about valence band and conduction band. Before going into the conduction and valence band, we must have a solid understanding of orbitals and shells. Pause the video if you want. Assuming you have some good understanding of shells and orbitals, let us get into the explanation. Atoms are arranged in a crystal lattice. The wave functions of the electron overlap to some extent, and there are a number of different interactions and disturbances that change the energy level of each atom. This means that the valence band is not exactly at the same energy as the free atom, but instead slightly higher or lower. This in effect looks and acts as a continuous energy band, not anymore as separate energy levels. Valence shell and lower shell interact and form a new hybrid shell. Each orbital in this shell is split into two by the interaction between atom in the crystal, and these two types are the conduction band and the valence band. The orbitals of hybrid shells are represented in lightweight dotted lines. The band is nothing but a range of energy orbitals, you can say. And the energy level that distinguishes these two bands is called the Fermi level. The Fermi level is the energy level that is occupied by the electron orbital at temperature equals 0 Kelvin or absolute zero. And the energy gap between the valence band and conduction band is called the forbidden energy gap. Above this Fermi level, that is the conduction band, where the electrons can freely move from one atom to another without much requirement or loss of energy. This is the reason why we call the band above the Fermi level the conduction band. Let us take silicon semiconductor at 0 Kelvin. The silicon acts as an insulator because of the higher forbidden energy gap, but the silicon can conduct electricity when enough energy is supplied to the silicon so that the electrons can jump from valence band to the conduction band. Here we are supplying energy in the form of heat. As temperature increases, the resistance of diode decreases. For metals, the valence band and the conduction band overlap each other, and there is no external energy required to make the metal conductive. As we see now, for semiconductors like silicon, there is the presence of forbidden energy gap, and we supplied energy to make the electrons jump from valence band to conduction band. Similarly, when electrons recombine with the valence band, they releases the energy that we supplied for the generation of conduction band electrons. The energy released will be in the form of photons or phonons, and these shown semiconductor materials are used to produce the required wavelength of light, and LED is represented in the circuit diagram as shown. Now we know all the basics to understand about the organic light emitting diode, that is OLED. In OLED, instead of using these semiconductor materials, we use organic polymers. Since these are long molecules, we cannot calculate the forbidden energy gap of all atoms inside the polymer because the polymer molecule is so big. So we use the difference in energy gap between highest occupied molecular orbital HOMO and the lowest unoccupied molecular orbital LUMO. We will not be discussing about HOMO and LUMO since it is beyond the scope of this video. It is just the energy gap. Similar to the normal LED, when electrons jump from higher to lower, that is HOMO to LUMO, energy is released in the form of light. And these are some of the polymers used in the industries. An OLED contains 4 major layers. They are anode, conductive layer, emissive layer, and cathode. And the shown polymers are used in emissive and the conductive layer. And these 4 layers are protected by 2 layers called the substrate and seal. Anyway, thank you for watching. Hope you enjoyed this video. See you in the next video. Stay tuned.